Hi everyone. Okay, Lauren is there.
Hello. Hello everyone. Thank you for being here, and thank you to the jury and the organization team for this award ceremony. I will be presenting along with Victor the project we worked on for the past year, the E4C challenge. The aim of the challenge, as Yves Bréchet said, was to imagine a solution to decarbonize cities and try to apply through a feasibility study this solution to metropole. We chose to tackle the reuse of wastewater energy in the city of Paris. We chose Paris because it seemed an easier case study to make because we were together, the data was easier. So to talk a little bit of the context and why we decided to tackle this subject, the first thing we realized was that water heating was a major cause of energy use. So as you can see, 40% of primary energy consumption goes into the building use in the US and in the EU. And 30% of that energy goes into water heating. The second thing we realized was that water heating energy was very carbon intensive. So as you can see, in the US and in the EU, there is kind of a lot of gas, a little bit of oil fuel, and you have electricity. So depending on the country you are, electricity is more or less carbon intensive, but here there is something that needs to be done about it. And finally, most of the heat in the wastewater was just wasted because throughout the journey they have plants, well, we lost a lot of heat. So according to the US Department of Energy, 400 billion kilowatt hour of hot water goes down the drain annually in the US. So we realized that wastewater was a new renewable source of energy. And so our main idea was to understand how we could recover this energy and how we could apply it to the city of Paris. Victor, your microphone is not on.
It's okay. So now I'm gonna present to you the approach we used for this project. So the first step was to properly define the scope of our study. This includes two main elements. The first one is the technologies. So by technologies, we mean the machines that can recover thermal energy from wastewater. The second element is the segments. So by segments, we mean the group of infrastructure where the technologies could be implemented. So by this step, we had to characterize, quantify, and size all of these infrastructure. Once we did this, we compared the segment potential in terms of energy, carbon, and economics indicators of each segments. This step helped us to conceive an action plan with a roadmap and the different steps that needed to implement these technologies in the city of Paris. And then finally, we assessed the impacts in terms of, again, carbon, and energy, and economics of the global action plan.
So in terms of wastewater, we identified three different types of, three different sources of energy: mechanical, thermal, and biomass. So the first two that we will focus on, so thermal and mechanical, involve physical processes that can be valorized physically. So that's the one we chose to explore. The last one is mainly based on chemical processes and is already valorized in a more central way. So mostly in the sewage treatment plant outside of the city. So as it is outside of the city, we considered that it was out of the scope of the study. So concerning the different types of water that exist, so here you can see 5 of them. As the subject is again limited to the city, we have excluded industrial and agricultural waters. We know that they have a great potential, but for example, industrial waters already been explored in different plants where they were used. So finally, we decided to work on gray waters and black waters. And the interest of domestic waters lies essentially in its proximity to the need and to the heat takers. And they also come under the responsibility of actors closer to the individual, with the possibility of smaller projects on the scale of neighborhoods or dwellings. And the runoff water have a very low potential, so we did not dwell on that. After examining the different types of energy, Victor, can you change it? Yeah. We analyzed the different location where we could take the heat from the wastewater. So here we are listing 4 different locations. So we have at the bottom of the building, so at the bottom of the flat for a household, for example, in the streets. So in the street is more the sewers or the collectors. And we have also at the lifting stations. The lifting stations are places where the level of the water is raised if the sewage is too low. And finally, we have the water treatment plant. So we listed the advantages and issue for each of those locations. Water treatment was a little bit far away, and a lot of heat was lost during the way, so we didn't consider that one. Lifting station is, well, the technologies for that are not very yet well explored, so we decided to stay on bottom of the building and the collectors.
So before I present the 3 technologies we chose, there are 2 concepts we wanted to clear. The first one is the concept of heat exchangers, which is an interface that allows a thermal transfer between 2 fluids. And the second concept is the concept of heat pump, which is a system that transfers thermal energy from a cold source to a hot source. So these are the 3 technologies we focused on. Biofluid, Degré Bleu, and Énergie d'eau. The difference between the 3 technologies is their position in the sewage system. So Biofluid is at the bottom of collective buildings with consequently quite pretty hot water, while Énergie d'eau and Degré Bleu are both positioned at downstream in the sewage system. The difference between Énergie d'eau and Degré Bleu is that Énergie d'eau is in total or partial diversion to the exchanger, while Degré Bleu is located directly in a series in the sewer. So we studied these 3 technologies and all their technical specificities to then link them to each segment.
So talking about segments, that's where we began to start the feasibility study for the city of Paris. So here we thought that the best way to lead this project was to separate Paris into segments of sanitary hot water. So as you can see here, we have the different segments we chose. We separated them into public and private segments because we thought that they had different acceptance rates from the actors, meaning that the public actors were more ready to accept new technologies or changes into the building, whereas private actors were more reluctant to pay more to change their heating system. So as you can, afterwards, for each of those segments, we had to calculate the volume of water that could be used for our system. And we compared it, our new system that we want to implement compared to the old system, and then measure the amount of CO2 emission we could save. So here I just added a small example about public hospitals and residential. As you can see, we have a penetration rate, which is very different for those 2 sectors, as I explained before. One of the hardest part of that work was to measure the volume of water, because that was a lot of data mining for us throughout many information we could get from different websites or different data sources. So it might be a rough estimation, but we still managed to find something. And Finally, so we had to find the type of heating which was already existing in those places. For example, public hospitals are linked to a heating network in Paris. So it's rather a good carbon emission heating, but we measured that our solution was still better than that one. And so with those measurements, we then were able to see if our solution was good in the city of Paris or not.
So based on the analysis we did on the segments and the technologies, we calculated several indicators. So here in the green table, you have all the financial KPIs. So the capex for the implementation of the technologies in different segments for the city of Paris. As the technologies are saving energy, they're also saving money, and that's why there are profits. And considering the fact that there are profits, we can also calculate the payback. What is positive here is that the payback is quite consistent with the lifespan of the technologies, except for the residential segments. So it means that for this segment, for this specific segment, there is clearly a need for subsidies to make this technology profitable. On the bottom left, you have the carbon indicators, and so the projected impact in terms of saved carbon for our action plan. What we see here is that we could reach about a tenth of the emissions of the city of Paris. So this is quite a positive result. Of course, it is a rough estimation. It's an order of magnitude, but what we see is that it remains quite significant. On the bottom right, you have the energy indicators. What needs to be reminded here is that we could save an amount of energy equivalent to about thousands of French households. Finally, what we want to really insist on is that we're conscious that this project has several limits. Of course, the results should be strengthened by the work of experts such as engineering firms. However, we quite remain convinced that there is a significant interest for the implementation of such technologies. The second point on which we want to insist is that there is clearly a need for a complete cooperation of all stakeholders. By stakeholders, we mean customers, engineering firms, local authorities, constructors. There's really a need for them to cooperate so that the action plan would be really efficient. This also means that there is a need for an intermediary actor that could be like between the consultancy and consulting and engineering team that could supervise the implementation of this technology in cities. Finally, we really want to thank Gilles Bordier, who was our reference from the CEA and who played a really balanced role and helped us all along the project. We also want to thank the jury for their congratulations. And finally, we want to thank the whole organization of the E4C Challenge, and especially François Willem. Thank you, everybody, and have a good night.